Okay, so let's see this in action. So let me run the program right here, and what you see is a very basic Mario program. He doesn't do much, he just moves left and right. There's no acceleration or anything fancy like that. Again, it might look a little jittery because you're looking at it at 10 FPS and this is running at 60. But what I wanted to show you is if I hit jump, he just jumps, pretty standard jump. Now, this is where the platform collision comes in. First of all, I'm doing platform collision right now. I'm standing on the ground, it's colliding with the ground and resetting me back on top of it. I do have a downward force, which is gravity pulling it down every time. But anyway, so let's check out the different things. So right now I'm colliding with my feet. If I collide with my, so I'll jump up and I can land on this platform. If I walk off the edge, doop, he automatically falls off. Because he's no longer touching, I'm still touching with my feet, and I'm not touching with my feet. So he falls off and he lands, keeps falling until he ends up on the ground and collides with another platform. If I jump up, and I can bounce my head off of this, right? So every single time he's just bouncing his head repeatedly. So he falls down back in the opposite direction immediately. And I also have it with the walls of the world too. There's a couple bugs in here, like I can just hold that up there. But anyways, it's not really the point. Same thing with the left and right wall. I can bounce off those edges. Right, so you can see, oh, I double bounce there. Excellent. See if I can do that again. I don't know. No. And I've had these little pipes up here. This is to represent the original Mario Brothers game, not Super Mario Brothers, where you actually have the pipes and the little creatures jump outside, like the crab and whatnot. Anyways, so this is what the whole idea of platforming boils down to. Depending on the type of game you're working on, this may be super useful or maybe not be useful at all. Now what you see here is just Mario. Now I'm going to hit my button, my T button, which is going to show test data, and that's going to actually show the rectangles I've broken Mario down into. So what you can see is you can see 4 colored rectangles. The yellow one on his head, which is actually slightly smaller than his head. So if I actually manage to pass through that corner, it's not going to even count it as a collision. Then I have the left and the right, so the green one and the red one, which represent his left and his right of his body. And then I have the feet. So what you can imagine is if I'm jumping, and even if I'm jumping to the side, if it nicks the side of the feet here, it's going to interpret that as a foot landing, which means it's actually going to, which is why I got that weird super jump there, because it kind of boosted me up on top of it, and I was still holding the jump button, so it managed to give me like a double jump right at that corner. But that's okay. That's a forgivable little mistake, not a big deal. And you'll notice that my foot box is actually smaller than the width, and that's just to give the illusion of walking off the edge a little bit more accuracy than like you're hanging on by your toes or something like that. Like that's as far over as I'm going to get. One more pixel and I'm falling. Okay, so that's how we break down the box. The code that I'm going to show you, I'm not going to show you everything because the jumping and the gravity and all that kind of stuff doesn't really apply to what we're doing. I'm just doing the testing. You can look at all the other demos to handle things like jumping and gravity and physics and all that kind of stuff, acceleration, in the other demos. That's not really the point of this. So we're just going to look at the meat and potatoes of the actual particle collision tests here. Or not particle, platform collision tests. So basically what I have is I've built my world up of rectangles. So all the platforms are in this array of rectangles. I also have an array of player rects, and these are the rectangles that I'm going to break the player's rectangle up into, so the 4 rectangles. Now you have 2 choices when you do this. You can calculate that those 4 rectangles at the very beginning and do the math and any type of multiplication you need to do once in the entire program. And then what'll have to happen is every time you move the player, and as well as their rectangle, you also have to move those player recs by the same amount to make sure that they're still in line. So that's more of a maintenance issue. The other option is to literally recalculate them every time you've discovered a collision with the bounding rectangle. So that's option 2. So option 2 is going to have more calculations on the whole, in terms of because you have to do all the redo all the math every time there's a collision, and there's going to be a lot of collisions because every time you're stepping foot on the ground, it's got to redo that. But option 1 causes you to actually maintain and update 4 rectangles every time you move. So you know it's a choice that you have to make. So I'll leave that up to you. All this other stuff is just to do with him jumping around the screen, so we're just going to ignore that for now because that's not really our point here. I've loaded all the content here, all the collidables. This is just me creating my different platforms throughout the world. And then the player and putting the player at a specific location. Nothing special here. And what I've done here is for player recs, I've called this subprogram called set collision rectangle. So what you can see here is that I'm actually calculating it once, and then I'm just going to update it every single time I move. So this set collision rectangle, set collision recs. Let's go down to find that code, which is right here. So basically, I have my array, and I have my top, my bottom, my left, and my right, and I'm calculating its x and y location based on the image's x and y location and the image's width. And so, for example, my x location for my top is 20% over from the edge, 20% of the width of the entire image over from the edge of the bounding rectangle. The y value is the same. The width of it is 60% of the entire image, and the height of it is a quarter of the entire image. So I've just done some little math, and I played with those numbers. So they're pretty much magic numbers at this point. But you play with them however you see fit, and you try and find the best fit for your program. But I do actually have rectangles here, which is why it's very easy for me to draw that data if I want to for testing purposes to make sure that I'm getting the collisions I expect to get. So I just continue this process for the other 4 directions as well. Now if you look up here, the order, top, bottom, left, and right, that's the priority order that I've set up. Top, bottom, left, right, because that's just the way I want to do it. You can modify that if you see fit. You are probably going to be colliding with your bottom more often than not, so it may be better to actually collide with the bottom first. So the update code doesn't do much. This is just moving the player around, so we're just going to ignore that. Down here, this is drawing the test data. So I just toggle it on and off based on whether the user hits the T key for test data. And we're just going to ignore the jump code. The move player code, we're going to take a quick look at that because that's going to update our rectangles. So we go down to move player. Where's move player? So move player calculates how much we should move in the X and the Y direction, and then it calls us translate player code based on how much it should move. And down here, what you can see is it moves the actual rectangle, but then it goes through a loop of all the player rectangles and moves them as well by the same amount. That way everything moves in sync. So that is the way that I've chosen to do it. I've chosen to maintain as opposed to recalculate, but it is a choice on your part. And then finally, at the end of all this, we do platform collisions with the player, all the player rectangles, and all the collidables in the world. So now there are ways to make this more efficient. You could say I'm only going to do my collision detection with collidables that are currently on the screen. Well, my little demo here, all the rectangles are on the screen. Your game may be a platformer, you're traversing through an entire level, so you may want to not waste CPU cycles and test anything that's off the screen, because that would be a waste. So going down to platform collisions, this is the way this works. Basically, I pass in the image, I pass in all the rectangles for that image, so the 4 pieces that we've broken it up into, and all the world rectangles, and I assume that there's no collision. By default, I'm going to assume there's no collision, so the only thing that's going to prove me wrong is if I find one. So inside, I'm going to go through every rectangle of the world. Go through each one. Step 1, check the current rectangle's image bounding box. So I don't do any of the work unless I find a collision with the bounding box and the platform. If I do, that means I go into the other pieces, which I have to check the other 4 pieces. So the order that I've done, the priority order I've done here in the actual testing is bottom, as I told you before, right, left, and then finally top. And that way, you're not even going to check these else ifs if you don't need to, because more commonly than not, you're going to be intersecting with the bottom of the rectangle. Basically what I do is if I land on the bottom, I stop jumping, I stop going through the air, and I translate the player, I move the player to the edge of the platform so they're standing on top of it, and I set found collision to true. Great. And then continues on with the rest of the platforms of the world. And the reason being, it's possible that you're intersecting with both a platform to the right of you as well as the bottom of you, so you can't move in either direction. So it's important that you go through all the rectangles of the world in this case. Basically, with the other rectangles, all I've done is I've flipped their direction if I collide with the left or the right. And again, I translate it so it sets it to the edge of the platform, so it's not embedded in the platform itself. And then finally, the top, it just flips the Y speed, which is the jump speed in this program, and starts it moving down. And again, it translates it, sets found collision to true. And then this found collision I just used to see whether it's in the air or not. So if I did find a collision, or sorry, if I did not find a collision, that means that I'm setting it to not in air. This is just for movement purposes and make sure that he's falling when he should be falling and whatnot. But that's it. That's all there is to it. There's nothing else here. You can see the intersect code is just the box-to-box intersection code that you've already seen. Nothing special. There shouldn't be too much more to it. I'm just going to quickly, for those that don't have access to the code directly and are just watching this video online, I'm just going to kind of quickly or slowly scroll through the code so you can see what's going on. And that way you can go through the video and check it out later on to try and recreate it yourself, if that is the case. So hopefully this algorithm will help you out and allow you to create your platforming game depending on what you're trying to do with it. Some games are much more complex. Maybe you're making a vertical platformer, maybe you're making a horizontal platformer, maybe you're making a single screen platformer like you just saw. It all depends on your choice. So that's platform collision detection. Good luck and enjoy.